Are we living in a video game? Is everything that we see around us actually just one big simulation? I mean, everything we observe, everything we experience, maybe that's being computed by some other, I don't know, alien race or some kind of higher power. If you look at video games today, they're getting more and more realistic. If you take a look at simulations today on the computers, they're getting more and more powerful. So realistic that sometimes you can't tell the difference, especially if we're talking about AI. So how do we know we're not in a simulation right now? Is that possible? Could we be living in a type of video game? This is the question posed by the simulation hypothesis, something that a few notable people do really believe in. You may believe in it yourself. We're going to take a look at that hypothesis in this episode, kind of prop it up a little bit, understand what its arguments are, and then I'm going to pick that apart and essentially argue in this episode that I think there's a lot of forced analogizing happening here, where you see analogies between whether that's quantum mechanics or other aspects of the computational universe we live in, and then you start to make connections to video games or some type of simulation. I think it's a bit forced. I think it gets something directionally wrong. But anyways, you may or may not agree. Either way, I think it's an interesting conversation. So let's go ahead and jump into the simulation hypothesis and see what you think. So, okay, there's kind of three main points you could say that the simulation hypothesis establishes or makes in order to come up with the hypothesis that, maybe we are living in some type of simulation or a video game. Okay, number one is that computers can simulate aspects of reality. True, that is true today. And again, like I said, if you look at AI, you can't even tell the difference a lot of times with the videos that they come up with. That's only going to get more powerful. So one, computers can simulate aspects of reality. That's absolutely true. Number two, future computers may simulate entire worlds. That's not totally unreasonable, although I guess it depends on how you define entire worlds. But computing power has exploded exponentially the last 50 years, right? Computers used to take up entire rooms. What's in your pocket on the iPhone or the Android is now more powerful. So another 100,000 years from now, if humans are still around, we can only imagine how powerful computers would be. So number two, future computers may simulate entire worlds. Yeah, I think it depends on how you define world, but not totally unreasonable. Number three, therefore, our world may be a simulation. That is essentially the simulation hypothesis in a nutshell. Computers can simulate aspects of reality. Future computers may simulate entire worlds. Therefore, our world may be a simulation. So why am I talking about this? Well, I just finished a book it's called The Simulation Hypothesis, and it's by the author Rizwan Virk. You may have heard of it. You may have read it. And it's an MIT computer scientist showing why AI, quantum physics, and Eastern mystics apparently all agree we are in a video game. That's kind of the parenthetical title of the book. But the book is called The Simulation Hypothesis. This is the second edition now, so this is something he wrote years ago. It was very popular. He's got a lot of feedback on it, I guess positive and some negative, but he came out with a second edition. And so I gave it a read because, you hear a lot about this, and Elon Musk will bring this up. He believes that it's possible we're living in a simulation. And it kind of sounds crazy, right? I mean, especially if you haven't thought about computational aspects of reality, if you don't know maybe much about quantum mechanics, or you just kind of never made that kind of metaphorical jump, right, between, let's see, what we know scientifically and then this idea that we could actually be living in some type of computer simulation. Okay, so let's kind of pick up, or let's establish what the main arguments in this book are, right? Do it justice. Give the author the credit, and then I'll kind of work against that a bit and say what I think is really happening, as I do in Science in Perspective. So the first one is this notion of quantum indeterminacy, and how that might say something about pixels. Okay, so the world does not appear, you could say, infinitely resolved, right? If you keep zooming in down to the smallest of small scales, which is what you do essentially in quantum mechanics, you look at the smallest of all scales and you say what's going on, right? Whether those are molecules, atoms, right? Anything in the nucleus, the neutrons and protons, the individual electrons, even smaller with quarks, maybe strings, right? You go down as small as you possibly can and you try to figure out how the world works at that scale. And what you see is not the kind of smooth continuity that we typically associate with what you might call classical physics, our kind of macro everyday experience, right? In other words, if I'm walking, going from A to B, or you see a car moving or a train, you don't see it kind of making these jumps. You see a smooth transition, right? It's kind of like a cartoon. Like if you watch a cartoon, or any video for that matter, right, it looks like a smooth transition. You're watching me right now if you are on video. But if you were to go to the individual kind of frames, I guess, right, the individual frames are kind of discrete, and there are actually jumps there. We just don't perceive them. So same with reality. This is what quantum mechanics tells us, right? There are quantized quantities, fundamental limits, and discrete structures, right? I mean, the common example would be if you zoom in on an atom and you take a look at what electrons are doing, they're not transitioning smoothly between their energy levels. They actually take these jumps, right? These quantum. So now, okay, so that's true, and that's what quantum mechanics tells us. As far as we know, that is absolutely correct about reality, right? Tons of experimental evidence suggests that it's true, and the theories all add up. Well, this can also feel analogous to, let's say, finite resolution in games, meaning if you take something like a video game and you zoom in, what you're going to eventually find are pixels. Okay, those of us that are a bit older know this very well, because if you played something like normal Nintendo, as we call it, the original NES, you can literally see the pixels, right? Or maybe you played Atari or something like that. You have these pixelated screens. I mean, even let's say the Nintendo 64 was a bit like that, but it was better. Eventually, you got to the point where you don't really notice the pixels, but they're still there. If you zoom in, anything on television is like this as well, right? There are pixels, individual, kind of squares of colors that are blending together at a higher scale when you're far away into something that looks smooth and continuous, right? But it is a finite resolution in those games. So someone from the, let's say a proponent of the simulation hypothesis is kind of making this connection. They're saying, well, take a look at physics, right? Not making everything up, just go to the science, and you see this quote unquote kind of pixelation in reality itself. Electrons make these jumps, right? There's this quantum indeterminacy. There's not this smooth transition between things. It's discrete. It's kind of like pixels. Okay, so that's the first kind of observation connection. The other one is if you take the notion of wave function collapse, this kind of seems like rendering in a video game. Okay, so talked about this in other episodes. You probably already know, but if you don't, again, quantum mechanics tends to kind of formalize or mathematize or envision, if you will, everything you know about a system in terms of a wave function. It kind of captures, right, the essence and the energies and everything you could kind of understand, let's say the positions, whatever, that's going on at that small scale. You could represent it mathematically as a wave function. And the wave function might not just be mathematical. It might actually be something that is real. We don't exactly know what that means, but maybe the wave function is something that really does exist in reality. You can kind of think of it as reality being smeared out as a probability. Let's go back to those electrons in an atom again. The electrons, in maybe your kind of first encounter with chemistry or something, you might have been you were drawing these as dots, kind of spinning around the nucleus as though it was a solar system. Of course, that's not what electrons are. They're more akin to kind of a smeared out probabilistic existence where you don't really know where the electron is at any given time, and maybe it isn't in any specific location until you actually go to observe it. This is one of those very counterintuitive things in quantum mechanics, particularly in line with the Copenhagen interpretation, where the reality might not exist until you actually go to observe it. And that observation, one way to think about that, it would be like the collapse of the wave function. So the wave function is smearing out the existence of something. It's kind of here, it's kind of there, it's very ill-defined. We as humans go make the observation, the wave function collapses, and then the very specific, let's say, location of that particle can now be rendered or perceived, right? So the role of observer and maybe in some sense consciousness itself seems to be kind of intertwined with reality itself, right? Now this is debatable. There's other interpretations of quantum mechanics. Not everybody agrees that this is how it works. But that Copenhagen interpretation is the leading interpretation. It's been with us the longest. It's stood up the longest. There are others, but that's just science right now. So quantum systems sometimes appear to acquire definite values only upon measurement, only upon observation, right? Well, it's kind of like a video game in some sense, and this is what proponents of the simulation hypothesis would say. If you think about distant scenery, it doesn't really get rendered in the video game until you maybe approach it and get closer, or more to the point, the scene that is off the screen isn't there until you move there. So again, going back to the original, let's say Nintendo games, it would be two-dimensional, but the scene isn't there until you go right, let's say, and then the scene comes into play. Now that scene doesn't necessarily have to, it can exist kind of just as information until it actually needs to be rendered. You don't necessarily have to pre-render everything. Today's video games, the more modern ones, that's definitely the case, right? Kind of think of it like Minecraft or something. If you don't turn your head, there's no reason for that part of the universe of reality to exist yet. We can compute so quickly now that when you go to turn your head, then the scene gets rendered. That's kind of like this quantum indeterminacy. That's kind of like a wave function collapsing, right? There's something kind of analogous there. The reality doesn't exist until you move your head and go to observe it, right? Which is like until you go to measure something. Okay, so that's quantum indeterminacy, kind of being analogous to pixels. There's wave function collapse being analogous to the rendering in a video game. Then there's also entanglement. Again, you can see there's a lot of quantum mechanics here, right? The thing about quantum mechanics is because it's so counterintuitive, you get all kinds of kind of crazy analogies and interpretations of what it might mean. People will start bridging it with like spirituality and consciousness, and who knows, maybe that's correct. It's just, I think it drives quantum physicists kind of crazy. They're dealing with this extremely counterintuitive aspect of science, one of the core pillars of science, the other one being general relativity, and or just relativity in general. And so they want to be rigorous and mathematical and scientific about it, but because it's so counterintuitive, you get a lot of people making these crazy connections. But who knows? Maybe the crazy connections are true. Right? Okay, entanglement is another one. That might be kind of analogous to hidden connections. So entanglement kind of exhibits correlations that seem difficult to reconcile with classical locality. In other words, and I've talked about this before, right? Go check out some other episodes. Again, you might already know it. It's kind of this, what Einstein called spooky action at a distance. You can debate whether or not that's really what it is, but basically there seems to be this long-range correlation. You could be literally light years apart, and maybe I go to some quantum particle, and then as soon as I know the spin on one particle, all of a sudden I know the spin on the other particle. It's almost like they're connected. They're somehow correlated. It's not communication, right? Communication can't actually travel faster than light as far as we know. But there's still this kind of spooky action, it seems, at a distance. So things seem to be correlated or somehow entangled regardless of the distance between them. It's a non-local phenomenon that seems to be happening. Other physicists will try to explain that using locality. But again, right, the leading kind of interpretation of what's going on here is this non-local thing. Okay, well, some people see a loose analogy with objects sharing hidden information in a simulation. So you can kind of go to video games or computer simulations, and you can say, well, maybe this is kind of like what happens. You're not limited in a video game, let's say, to something only being super local, right? Like, I don't know, your video game might teleport you to another area of the game, and it can do that immediately, or some other type of entanglement or spooky action at a distance. There's nothing, right, in the so-called physics of the video game that's limiting that, and we also see that in quantum mechanics. So again, there's a connection there. Another one is wormholes, right? And that's kind of like the teleporting in a way, maybe, right? There's shortcuts that can happen. There is speculative connections between entanglement and space-time geometry, ER equals EPR, if you want to get into the physics of it. And it kind of evokes the idea of shortcuts through an underlying computational architecture. These are actually called Einstein-Rosen bridges. We're not going to pick all that apart right now, but wormholes are theorized to potentially actually exist. They're, I guess, usually you'll kind of see someone make this analogy or this kind of intuitive visualization where you take a piece of paper and you fold the piece of paper, and where the piece of paper touches after the fold, you poke a pencil through it and say that's kind of like a wormhole. So the paper would be like the fabric of space-time, and you would normally assume that you have to traverse the distance of the entire space-time. But if space-time can fold, which presumably it can, if it could fold extremely, then maybe it folds so much that 2 points actually come together just like the paper, and you could travel through those 2 points of the fold, and it would be like instantaneously traveling a very large distance, right? You see this in science fiction a lot, all the time. Star Trek, Deep Space Nine, kind of Star Trek in general. The newer ones especially, they play with this idea of wormholes and traveling far distances, way more than even superluminal or faster than light would be able to do. So theory kind of adds up. You can take a look at relativity and you can kind of bridge that with quantum mechanics. Some people think maybe that is the way to bridge it with quantum mechanics. Anyway, wormholes, see in science fiction, there is some real science, at least theoretically. And again, in a video game, you can kind of teleport or transport to areas virtually instantaneously, so maybe that's kind of analogous. And then, aside from looking at the science, you have Western and Eastern religions. Again, these are kind of the core arguments being made in the book, right? And so, again, now we're making analogies to religions. How does that work? Well, you can kind of think of, especially in Eastern religion, kind of this overarching theme with a lot of them, the world is kind of an illusion. In fact, all of them in some sense maybe think that. Like the world that we live in is more illusion, right? It's not really what's important. It's not the real thing. You can be in the world, but not necessarily of the world. Maya in Hindu traditions, for example, right, would kind of see the world as illusion. The distinction between appearance and underlying reality in Buddhism. The material world is kind of a lower order reality in some Gnostic traditions. There's Plato's cave as a world of shadows, right, mistaken for reality. There's these kind of mystical traditions that describe ordinary experience as more of a limited projection of a deeper reality. And the book talks about angels and demons and all this kind of stuff. And the book's not saying it's definite, but he's saying, if you take a look at what a lot of people in Western and Eastern religions have been talking about for thousands of years, and you don't just discount it all, you say, well, look, maybe there's something there. There's a lot of experience that survived the test of time over thousands of years. The materialistic view of science doesn't have much to say about it, but maybe there's something there. Well, maybe the simulation hypothesis is a way to kind of make sense of what's being talked about in the religions. So, okay, so that's what that. So we've got the quantum indeterminacy, we've got the wave function collapse, we've got entanglement, we've got wormholes, and we've got Western, Eastern religions. You can take a look at a lot of what we've been talking about in science and religion, and maybe the simulation hypothesis is kind of a way to reconcile that or give an explanation for what's happening. Okay. So what do I think? Well, I want you to, I don't know, you don't know, maybe we are in a simulation, right? Maybe those analogies are more than just analogies. Maybe, yeah, there's almost a kind of pixelation when you look at quantum mechanics. There's this kind of observer effect where it's almost like, reality, maybe, at least under the Copenhagen interpretation, maybe it doesn't get rendered until you actually look at it, right? The moon isn't there unless you look at the moon. Maybe, right? But notice that the simulation hypothesis argument kind of quietly imports an analogy between computers inside reality and reality itself. Okay? So like, yeah, I mean, so like, what are we, is everything that we're in one big simulation a computer? But then we also have computers in reality that we build, and they're using that as the analogy, but then they're saying all of reality is a computer, so you don't need the computer inside the computer. Something's kind of off here, I would say, right? In terms of the analogy making. There's kind of a breaking here. And here's the point I really want to make in this episode, is that reality is already a computational process. That's actually quite widely accepted. We're going to get into that. Without evoking anything about a simulation hypothesis, yes, reality is quite computational. And I think what the proponents of the simulation hypothesis are doing is they're kind of getting surprised that science is saying, oh, look, reality is kind of computational. And saying, oh, well, it's really? Well, then maybe we're actually in it. They make this leap to simulation, like maybe reality is a simulation. But just because reality is computational, which actually isn't that surprising at all, which we'll get into, it doesn't mean that therefore we're in a video game, or therefore in a simulation, right? There's this kind of mistake being made. I think the proponents of the simulation hypothesis are viewing computers only in the way that we think of kind of Turing machine computers. They're thinking of that as computation, and therefore if reality is doing computation, it must be like a... Anyways, I'll break apart the differences there and say why I think it's a stretched analogy. But look, reality is already computational as far as we know. That's not surprising. Many scientists, as we'll see, believe that, and for good reason. So there's no need to posit an additional computational substrate underneath, is what I'm saying, right? It's not like, oh, look, there's these surprising things that look computational reality, therefore we must be in a simulation. It's like, no, reality is just quite computational. That's a very natural thing. You don't need another substrate. You don't need another alien race to have been computing what we're experiencing, or some other, that's what I mean by a substrate underneath. You don't need like another computer for the computer we're in. Reality is quite computational. Okay, so let me give you some examples, and hopefully that'll make sense. Okay, first of all, bare bones, let's take computation in the most kind of like obvious, brutally kind of obvious or abstract way, but still true. So when a planet moves according to gravity, we can describe it as computing its next state. That's true. That's not a crazy thing to say, right? But that doesn't imply the planet is running inside a computer. Okay, you don't like that example? Okay, we'll take a tornado. Actually, I've used this one before, right? A tornado is doing a type of computation. Of course it is, right? Because there's this outstanding problem of trying to balance high and low pressures between different elevations, and the tornado is the solution to that problem, right? You wouldn't relieve the various forces that need to be balanced, if that's how you want to say it, if you didn't have a tornado to eventually relieve that tension. That is a type of computation because you're transforming one state into another state. There's an input being transformed into an output, right? Even just like a static mountain or seemingly static mountain that stays there is doing something with airflows and air direction that does solve a problem. Okay, and so likewise, take whatever example you want in nature, right? If the universe transforms states into subsequent states, well, that is already a type of computation in the broad sense, right? It does not automatically imply a programmer, hardware, software, or any kind of simulation layer, right? That's just computation. And that's not crazy. That's not me pushing that. That's actually pretty widely accepted, right? Physical systems process information. Now we're going to go to a deeper level here because you might say, yeah, that's a super kind of high level, general, almost goofy version of computation. I mean, I don't know if that's really computing. Okay, well, let's go lower into it. Physical systems are definitely believed to process information, right? A thermostat, a cell, a brain, a weather system, and a quantum system, they all transform states according to physical laws, right? It is what computation is. You have an input, you have a transformation, and you have an output. You have states changing through transformation. Okay, let's go further. Okay, many natural systems can be understood as performing computations, right? The nervous system is absolutely computing responses, right? Gene regulatory networks are computing cellular behavior. Immune systems are computing threat responses. Ecosystems are computing, you can say, population dynamics, right? In fact, there's even an entire field called natural computation devoted to studying such processes. Nothing to do with simulation hypotheses, just recognizing that, yeah, it's almost pretty obvious that nature is doing a type of computation. It's quite computational. It's transforming information. There's inputs converted to outputs, right? You can take a look at, there's a paper, called Computation by Natural Systems by Xu and others, and it talks about how computation is an extremely useful concept, far beyond just kind of the usual disciplinary boundaries of computer science, and it goes on and talks about that. There's many areas within science that believe the universe itself may be viewed as a computational process. You've got digital physics, right? You've got a type of computational natural philosophy, it's called. You've got information theory, right? Information theoretic physics that really frames everything in terms of information. And information doesn't just sit there statically, it gets processed. And the information that's getting processed, of course, is in some sense a type of computation, right? And there's other related frameworks, right? You can take a look at another paper, related computational natural philosophy, right? There's one called A Thread from Pre-Socratics through Turing to ChatGPT. So it's very up to date, it's very relevant, frames things in terms of computation. And keep going on, right? There's other papers. Actually, a quote from the paper, another one is that all physical systems process information and can therefore be considered as performing computations, right? That's from Science Advances, a paper called Computational Capacity of Life in Relation to the Universe. Okay. Keep going, right? Keep pushing on this, right? Like I'm trying to show you, and hopefully at least somewhat convince you that this is not surprising. I mean, there can still be surprising aspects that maybe nature is computing, but it's really not a stretch. Information is an absolute core, right up there with quantum mechanics and relativity, quite frankly, as being a fundamental aspect of the way that we describe reality. In fact, a third pillar could be called thermodynamics, quantum mechanics, relativity, and thermodynamics. I've talked about that a few episodes in the back, and tied in with thermodynamics is absolutely the role of information. And again, information is being processed and being transformed. It's converting things into other things. I'm sorry, but what else are you going to call that other than computation, right? There's a 2026 special issue in the Journal of Physics Complexity that was devoted entirely to the question, with researchers explicitly discussing how to identify computations occurring inside arbitrary natural dynamical systems. Again, we're not talking about simulation hypothesis. We're just talking about the computation in nature, right? So look, serious scientists are not asking, can nature compute? They're actually asking, well, how do we rigorously characterize the computations that natural systems do perform. It's just kind of accepted, right? Now, I'm not saying there's no debate here, but I mean, it's just, this is not a weird, crazy, surprising thing or a niche area of science or a recent thing in science, quite frankly, right? You can keep going, right? There's John Archibald Wheeler. You can go read his It from Bit. There's Ralph Landauer, right? Information has physical consequences, right? It's almost like information is physical, right? Seth Lloyd, looking at how the universe is essentially a quantum computer. There's Edward Fredkin, digital physics and computational universe ideas and all this kind of stuff. Okay, so I mean, I just want to impress upon you, right? Like, it's not out there that, oh my goodness, maybe the universe is computing. Yeah, of course it's computing, right? I mean, I say of course, and you maybe you think that's a bit strong. I don't think it is. I mean, in some sense, for sure, it's computing. Of course, there's information. It's a very, at least useful, if not absolutely realistic way to look at the universe. And of course, the information is getting transformed. What is it you think a computer is doing, right? So the simulation hypothesis treats reality's computational character, which is already widely accepted by many, if not most scientists. It treats that as evidence that it is running on a computer. Well, but this only follows if one assumes that all computation requires an external computational substrate, as I'm calling it, right? Physical systems already perform state transformations intrinsically, though. So why do you need something external? Why do you need the extra substrate? Why do you need a computer outside the one computer? Why do you need the alien race or the advanced civilization to make the simulation? Nature is computational. It is processing information. State transformations are happening intrinsically in brains, in cells, in quantum systems, in mountains. I mean, that's what nature does. So I don't understand the stretch where now we kind of need to invoke something extra. It's not particularly in line with Occam's razor. It's not particularly simple. You need to admit a lot of these assumptions that don't seem particularly well founded. So I'm arguing that computation is simply what physical systems do. A system transforms information according to its own structure. There's no external substrate or alien race or higher power or substrate required to make that happen. That doesn't mean there isn't. It's not required, right? Just by the facts, right? So my argument in this episode is essentially, if I had to put it into 5 points, I say, like, well, one, I mean, because we went over the simulation points. Here's my points. I say, one, scientists increasingly view nature as computational. That's true. 2, computation is therefore not surprising. 3, the simulation hypothesis treats computation as evidence for simulation. 4, but computation is already expected if reality itself is computational. 5, therefore, reality looks computational is not evidence for simulation. And that seems to be where the proponents of the simulation hypothesis are getting their arguments from, right? So people often conflate two very different ideas. There's the computational universe, right? Which is what I'm saying. Like, yes, reality is fundamentally information processing, right? Input leading to output. There's those transformations happening, right? And we saw, I just kind of went at you with many examples, right? So I don't need to do that anymore. And we saw how this idea appears in various forms, again, in digital physics, cellular automata, information theoretic physics, right? Complexity science, it's everywhere, right? And then you take a look at the simulation universe, the other thing, right? Where reality is being computed by something external to itself. There exists a host substrate on which our universe runs. So it's confusing, those two. It doesn't make sense. The first, I would argue, the first does not logically imply the second. The idea that the universe seems computational does not logically follow from that therefore we're in a simulation. Right? It's an unneeded injection of assumptions that just it's not needed for the model, right? So a weather system computes its future evolution, a brain computes responses, an ecosystem computes population dynamics, yet we do not conclude they are simulations. Right? So why should computation require an external computer? This is what I think the fatal assumption is inside the simulation hypothesis, right? In other words, the universe is not like a computer. The universe is the thing from which the concept of computation was abstracted in the first place, okay? You have to understand that, right? The universe is the thing we were looking at as scientists and saying, look, this seems like computation. I think this is computation. Our whole notion of what computation is as a word was abstracted from looking at the reality of nature, right? So the universe is not like a computer. The universe is the thing from which the concept of computation was abstracted in the first place. I mean, after all, we invented computers by observing regularities in nature and engineering systems that exploit them, right? Computation came from observing reality, so there's little reason to assume reality itself must be from someone or something else's computer. Where does that come from, right? So the simulation hypothesis may be committing a false analogy by taking human-built computers, which are embedded within reality, and projecting their architecture onto reality as a whole. Okay? Now, there are probabilistic arguments or statistical arguments that kind of get made, and I would say this is probably the strongest kind of simulation hypothesis. This is probably the strongest argument that proponents of the simulation hypothesis can make. I'm not saying I agree with it, but it's at least it's got something, right? And the strongest simulation hypothesis advocates usually avoid the criticisms of others and might, for the ones that I'm making, by appealing to probabilistic arguments such as those associated with Nick Bostrom, right? It basically says that if it is possible to simulate full realities, like if it's just possible to do it, then it's statistically more likely that we are in a simulation than in some original physical reality. I mean, I kind of like that. That's not a bad argument, right? It's basically saying, just assume that it might take us 1,000 or another million years, but let's say it's possible, which was the second point of the simulation hypothesis I said at the beginning. And I said, yeah, I mean, that's not crazy. Maybe it's possible to simulate physical realities, right? Something extremely realistic that could at least fool us. AI is already fooling us with conversation. The Turing test is all but passed. I don't know, maybe, I mean, physical reality is another big leap, but again, we can create videos. There's augmented reality, there's virtual reality. They're hardly there yet, but again, another 1,000 years. Okay. So if that is possible, and it's kind of easy to spin off simulated physical realities, or just simulated realities, then just statistically, wouldn't there be a lot more of those than there are original natural physical realities that people who don't buy into the simulation hypothesis think that we're in, right? And then, so just statistically, just by the numbers, it's like maybe we're just in a simulation. That's not a bad argument, honestly, it's not. But even then, right, the argument depends on assumptions about civilizations, computing resources, right? A lot of people say, and the book deals with this, right? Kind of say like, well, you probably need at least as many atoms in the universe just to compute the simulation of the universe or of the Earth or whatever it is, even just of the Earth maybe. And so like, what's the point, right? And then the author of the book will kind of bite back at that as some others will and say, well, yeah, but maybe the scene doesn't need to be rendered until you look at it, right? And maybe the universe is kind of running optimizations like that, so you don't actually need all the atoms. But you're still making a lot of assumptions, right, about civilizations wanting to do this in the first place, able to do this in the first place, computing resources, right, and substrate independence, which is my biggest pushback, that remain highly speculative, right? So, look, the fact that reality exhibits computation does not support the simulation hypothesis, I would say. Computation is not evidence of simulation because physical systems naturally compute their own evolution. The simulation hypothesis, it really only follows if one assumes that computation must occur on some deeper external substrate, and that assumption has not been established. Right? So I propose kind of a reversal of the usual framing we hear from the proponents of the simulation hypothesis. Right? So the simulation advocate would say reality appears computational, therefore reality is probably running on a computer. My response is reality appears computational, right? Therefore, computation appears to be an intrinsic property of reality itself. In other words, the same observation points in the opposite direction to what the proponents of the simulation hypothesis are arguing, right? So the deeper issue is that, simulation advocates often treat computation as if it were evidence for some kind of host substrate, right? Some bigger computer that's running our own, let's say. But where did our notion of computing come from in the first place, right? We did not discover computers and then infer nature. We observed nature and then invented computers. So I think they get the direction wrong. Okay? So if you discover that nature is computational, the most parsimonious conclusion is computation is a property of nature, not nature must therefore be running on somebody else's computer, right? Occam's razor exists for a reason. We try to prefer the simplest theory, not just because simple is right, but because simple is easier to validate, it's easier to falsify, right? So the more kind of parsimonious conclusion you could draw, the thing that's going to admit the least amount of assumptions is that computation is just a property of nature. Okay, not nature must therefore be running on somebody else's computer just because you discover nature's computation. It's this whole other level that seems completely and entirely unneeded. And again, I think it stems because maybe people that are not as exposed to, I guess, the information kind of theoretic side of science that is already in many different areas looking at nature as though it is basically computing, they tend to get surprised that nature seems like a computer, and then they jump to this analogy and they stretch that out to simulation hypothesis. Let's think about analogy, right? Like, imagine someone notices that rivers solve optimization problems, which they do. That's not crazy. It's not like some stretched analogy. Of course they do. Right? Water finds efficient paths downhill. It's an optimization. River networks often approximate solutions to transport problems, right? So let's say you notice that, but then you conclude, since rivers perform computations, there must be a giant river computer underneath every river performing those calculations. Maybe, but that would be a pretty strange inference, right? The more natural conclusion is obviously that the river itself is the computational process. I don't think it's really harder than that, right? So likewise, the universe itself may be the computational process. You don't need to invoke anything else, right? Now, none of this proves the simulation hypothesis false. I don't know. You don't know. Yeah, maybe we really are inside a simulation, right? We really could be inside a simulation. But what I am showing in this episode is that, the observation that reality looks computational has no discriminative power between, one, reality is fundamental and computational, and two, reality is simulated and computational. And that's what you need. You need some kind of discriminative power between those two things. Otherwise, you're just mushing them together with very loose and forced analogies, which I think is what's happening here. So my point is that, the first explanation that reality is fundamental and computational is simpler because it requires fewer ontological commitments. Whereas the second, reality is simulated and computational, is got all these assumptions and ontological commitments that you need to make that just don't seem particularly well-founded. But I could be wrong. Let me know what you think. Do you think we're in a big video game? Do you think we're in a simulation? Do you think when proponents of the simulation hypothesis are making these analogies to what you see in quantum physics and what you see in Eastern and Western religions, is there a real connection there, or is that just kind of reaching and getting a little too loose with analogies? And is it actually true that, look, yeah, nature is computational, and that's that? We discovered computers by looking at nature. It wasn't the other way around. Anyway, that is it for this episode. Thanks everyone for listening. Those of you who are watching, for those of you who want to get more into this kind of stuff and really try to understand some of the science behind it, still conceptually, but get a little bit deeper, go ahead and check out my app on Dekion, Dekion.io. There's the link, and I'll put it in the description. It's always in the description as well. Dekion.io /Sean/Science in Perspective. And you'll get access to the transcripts. You'll get these nice data visualizations of the concepts that I talk about and how they relate to each other. There's a study space. You can even test yourself conceptually on some of these ideas. Really kind of dig into it. Just expose yourself to more of this information and this knowledge. There's a community forum on there. There's an AI chat feature where you can chat to AI about this episode and across episodes, because it's built so that it's aware of all the episodes that I talk about in Science in Perspective. Make interesting connections. Keep asking, what did Sean mean when he said this? What does this mean? And all kinds of other interesting stuff. Summaries and techniques and mindset articles and all that kind of stuff. So go ahead and check out Dekion.io /Sean/Science in Perspective. Become a member today and get a lot more value out of these episodes. Okay. Thanks everyone. Until next time. Take care.